Well, here we are, Bio 30. This is video number 2 about pedigrees. So in our first video, we went through the symbols that is used and how to refer to the individuals on a pedigree. And we talked about the mode of inheritance, how to tell apart recessive and dominant. We talked about recessive. So next, I have given you a blank pedigree. Here is a pedigree that it has a bunch of generation numbers on it, and the individuals are numbered, but it doesn't tell you the mode of inheritance. So you have to ask yourself, is it recessive or is it dominant? And this one is a dominant trait. So how did I know that? How was I able to figure it out? Again, we begin by looking at the offspring, and you work backwards and look at the parents. So to me, I kind of look through here and I see here's an affected female, 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 male, male, male. It's about equal. There's 3 females that have this trait, 3 males that have this trait, but that doesn't help me to decide, is it recessive or dominant? I have to decide by using this criteria. So is there any unaffected child with 2 affected parents? So let me look. Oh my, look at this child. Individual 2-4 is not affected, yet each parent is. How can that be? If this was recessive, remember how we just did the recessive for earlobes? There's no way that this child could not be anything other than little e, right? If you have both parents homozygous recessive, that child has to be homozygous recessive. So this can't be recessive. This has to be a dominant trait. And that child, 2-4, is the key to the entire pedigree. The thing that you'll find in dominant is that you will see it's the exact opposite of recessive. A child who does not have the trait, yet both parents do. And so how can that be? Well, it has to be a dominant allele causing this trait. Unaffected child, yet both parents are affected. Again, that's not possible if it's recessive. So if this is a dominant trait, and we're going to use polydactyly as our trait here, which means you have extra fingers and toes. People can have this, and also cats can have this. Now, I want you guys to understand, dominant is an allele. It's not how common something is in the population. Like seriously, how many people do you know that have extra fingers and toes? You probably can't even name one. So because it is dominant does not mean that you're going to see lots of people that have the trait. It just means that it is an allele that is going to be dominant to or overpower the recessive. So this is the dominant allele, having polydactyly, extra fingers and toes. The little p is the recessive, and that's having normal fingers and toes, not extra numbers. You're not affected by polydactyly. So here's this individual, and this individual obviously is not shaded in. So they do not have this trait of polydactyly. Everybody else who is shaded in, we're giving them a big P. They have the trait of polydactyly. They're affected with extra fingers and toes. 2-4 has to be little p, little p. They are not affected. They're not shaded in, so they're not affected by extra fingers and toes. So how did this kid come about? How do we have an unaffected child, yet both parents are affected? Well, guess what? This parent was heterozygous. They had that little p, the normal allele, and same with this parent. They had the normal allele. Now, can I call this person a carrier because it has a little p allele? No, this is a dominant trait. They have the trait. They have the big P. They're shaded in. They have extra fingers and toes. They're not carriers. They have it. They're affected with it. They are heterozygous. Okay, so be careful when using that terminology. A carrier is only used if they carry a recessive allele, but don't show the recessive trait because the dominant is going to protect them from it. When you have the dominant trait, you have the dominant trait. You're not a carrier, right? You have it. You are affected. So this is key here, this unaffected child having two unaffected parents. Another thing you should look for is that the trait will not skip generations like it did with the recessive. People have it in generation 1, people have it in generation 2, people have it in generation 3, except in this family. Look what happens here. Here, it disappears entirely from this family. Everybody now has little p, little p. Not a single person has the big P allele, so not a single person has that polydactyly. Another thing you're going to notice is that if you have a child who's affected, shaded in, they have to have at least one affected parent. So 2-2 here and also 2-3, each of them has a parent who is affected. Here, 3-4, they have at least one affected shaded in parent. So this is an example of a dominant trait. Were there more people that had it than didn't? No. So again, this is not a recessive trait. You can't have two recessive parents have a child that's not recessive. This has to be dominant. And again, don't confuse dominant with how likely it is that you get a trait. Right? When we're talking about how often people get a trait, don't just go and count them up and think, oh, if there's lots of people that have it, it must be a dominant trait. That's not true. There are some families that have a high amount of carriers and affected individuals, but it's a recessive trait. So I want you to think of blue eyes. Blue eyes is a recessive trait. Brown is dominant to blue in eye color. Now, it's very complex eye color, but blue eyes is a recessive. Now, I want you to think of Scandinavian people, people from like Sweden and Norway. And what do you picture? You picture blue eyes, right? So there's lots of people that have blue eyes, but that does not mean that it's dominant. It's a recessive allele. Why do so many people have it? Because there's lots of carriers and affected individuals in that population that are breeding together. So a dominant allele just simply means that it is going to overpower a recessive allele. It has nothing to do with how common a trait is in the population. So please keep that in mind. Don't just look at a pedigree and say, oh yeah, lots of people have it, it's dominant. That's not true, and that's not correct justification. That is a misconception. Okay, so next I'm going to talk about how do I know if a trait is autosomal or if a trait is going to be X-linked. So in this, you may have a recessive autosomal or a dominant autosomal, recessive X-linked or dominant X-linked. But the key to these ones is to look at the ratio of males and females in a particular pedigree. Now, again, that's not your best reasoning. That's your first glance. So you start by looking at the pedigree and counting up how many males and females are affected, shaded in. So looking at this one, again, start with the offspring and we're working backwards up to the parents. Is there a fair amount of people affected? Yes. Does that mean it's dominant? No. This is a recessive allele. How do I know that? Because look at, here's an individual affected, neither parent is. So clearly this child is receiving the allele from an unaffected parent. That means at least one parent must be a carrier. Now, this Victoria should actually have a little dot inside, a little circle inside there. Now, guys, look at the male-female ratio here. There are 11 males on this pedigree that are shaded in, affected with the trait. No females. This should be your first clue that this has something to do with the X chromosome, right? Guys only have one X chromosome. So if they receive an allele, like the hemophilia allele, and they don't have a second X, they're going to express that trait. They're going to get hemophilia. A female sure could have that hemophilia allele, but reminder, she has a second X. So she has the normal that overpowers, it's dominant to that recessive. She's not going to have hemophilia. And so this is very clearly an X-linked trait. And so, yes, it's good to just start with your first glance at the number of males and females affected, but there's more to it than just that. You have to assess a couple more things than just, is it all males or is it all females? Okay, so I'm going to make a third video in this series. I'm going to cut this one a little bit short. I just don't think I'd have time to finish all of this in the next video. So again, this is video 2 of our pedigrees series, and I'm going to sign off for now, and we'll talk later. I'll have at least one more video in this series.